Welcome back everyone. In this lecture I will actually introduce some arithmetic groups coming from elementary number theory. So, first we will see a group actually that can be constructed using addition modulo n. Okay. So, for that let me just motivate from the scratch. So, let us start with this group of integers. So, this is the group of integers. So, now let us fix some number and then just work out some details related to the number. So, let us begin with something very simple. Maybe we can take for example n equal to 2 and then see what happens. So, if we take n equal to 2, we have a natural subgroup defined by that 2, which is 2z, the set of all even integers. So, this is actually a subgroup of integers. But the thing is, this 2z is indeed partitions z into 2 sets. Okay. So, what it does? So, you can write z as 2z union 1 plus 2z. So, what is 1 plus 2z? So, those are all odd integers. Okay. Basically, this is even integers and this is odd integers. So, what is addition modulo 2? Okay. So, what is the meaning of doing some arithmetic modulo 2? So, this is about the things that you already been familiar with adding even integers or odd integers. So, you must be knowing already if you add 2 even you get even. So, that is what called addition modulo 2. Okay. So, I will just write down the formula. Even plus even, you already know it is even, and then even plus odd, you know it's odd, and then if you take odd plus odd, then it must be even. So, this is something all of you know. Okay. Basically, what is encoded here is called addition modulo 2. Okay. So, what we indeed do in this addition? So, basically when you add two even number and then we are saying that we get even number. Basically, what we are doing, we divide that number by 2 and then indeed we are adding the remainders. Okay. And then seeing what we are getting. Basically, if you take even number, if you divide by 2, then you get remainder as 0. Okay. Then if you add 0 plus 0, it becomes 0. If you take odd number and divide by 2, then you get the remainder 1. Then if you add for example even number and odd number, so then basically you take the remainders which is 0 and then 1. If you add them, 0 plus 1 will become 1. So, that is odd number. Similarly, when you add two odd numbers, so that becomes 1 plus 1. So, which is again even. Okay, that actually becomes even number. Okay, that is what exactly you are doing here in this. So, this is something we can do with just with this sets itself. Okay, because this 2z is actually a subset of z and this 1 plus 2z, this is also a subset of z. So, what we can do, we can actually just try to add them, subtract them and then see what happens. So, why I can do that? Suppose I start with AB inside z, they are subsets, then I can define what is called A plus B. So, what naturally what is A plus B? This is all possible A plus B, where A is coming from capital A and B is coming from capital B. So, you can take all of them. Okay, that it is meaningful to call that set as capital A plus B. Okay, it is well defined. So, this already motivates us to do the arithmetic. For example, I can also call what is this integral multiple of A. So, this is also I can take it to be just a Ka, where K is coming A is coming from capital A. So, similar thing I want to do here. So, whatever encoded here, when you say even plus even is even, basically what you want to say, you take some element in 2z and then another element in 2z and then you try to add and then see what happens. So, when you look at it as subset of z, then you can see that this is exactly 2z. So, that means it consists of even numbers and exactly all even numbers because 0 is in 2z. Okay. Similarly, if you take 1 plus 2z, so which is odd, and then if you add it with 2z, then what happens? As a subset of z, you can see that this exactly becomes 1 plus 2z. Basically, you take odd number and even number, you add them, you get odd number. Okay. So, similarly, so what we are doing, you have taken 2z and then 1 plus 2z. So, this I can consider as one set. Okay. Basically, this is living inside power set of z. Power set of z consisting of all possible subsets of z. So, 2z and 1 plus 2z is one such subset of power set of z. So, what we are telling? We are telling that 2z plus 2z, if I add, I get 2z, and then if I take 2z plus 1 plus 2z, then you are getting 1 plus 2z. Similarly, if you take 1 plus 2z and then 2z, you get 1 plus 2z. Similarly, if you get 1 plus 2z, 1 plus 2z, so then you are getting 2z, okay, because 2 plus 2z again 2z. So, if you take this set, okay, and treat it as 2z and 1 plus 2z as elements of that set, so then induced from the addition that you have already in the integers, induced from that you have some well defined addition between these two elements. Okay. So, like you can add them and so on, 2z plus 2z makes sense, 2z plus 1 plus 2z makes sense and so on. So, this is somewhat, so this is the abstraction that you are supposed to appreciate. So, when you think group as a set, non-empty set which has some binary operation satisfying some properties, okay. So, then I am allowed to take that group as anything that I want, as long as I can actually define binary operation that satisfying associativity, existence of identity and existence of inverse, then I am in the business. So, that is what we are trying to do here. Even though this is just a set already coming from the subgroup z, on these sets, okay, when we treat it as elements, we are able to perform some operation, binary operation, which is again we denote it by addition plus. Okay. So, this is what somewhat motivates us to actually do what is called this arithmetic modulo 2. Okay. Because this 2z I can treat it as 0. So, instead of remembering 2z, I can remember what it corresponds to, what remainder it corresponds to. Okay. When I divide by 2, you see that whenever you get 0, that corresponds to even integers. So, the remainders when you get 1, that corresponds to 1 plus 2z. So, we already seen using division algorithm, whenever you divide by some natural number, then you get a remainder that is between 0 and n minus 1. Okay. Here it is 2. So, you get remainder from 0 and 1. Okay. So, that means instead of thinking it as 2z, I can think it as also 0. There is no harm in it. I can think this 1 plus z as 1. There is no harm in it. Okay. But these things we want to make it more precise. So, basically that is all about arithmetic modulo n. Okay. So, let us try to do one more example and then I will convince you that what we are really doing. Okay. Let us take now n equal to 3. Okay. So, then you see that this z is actually splits into 3z, all multiples of 3z, 3, and then some numbers that leaves 1 as remainder. Okay. So, this is a disjoint union, and then disjoint union some numbers that leaves 2 as remainder when you divide by 3, because these are all the only possibilities, because we already said when you divide by 3 the remainder must be unique and it is between 0, 1 and 2. Okay, it must be less than 3. So, you collect those that are actually gives you 0 and those that gives you 1 and those you gives you 2. Okay. So, now let us take these things and then try to add and see what happens. If I take 1 plus 3z as before, I can try to add it with 2 plus 3z. So, as a subset of z, you can see that this corresponds to 1 plus 2, which is 3. So, it is 3 plus 3z. So, which is just 3z, because 3 is divided by 3. Okay. So, somehow you can actually write down everything here and then see what happens. So, this is what somewhat birthplace of addition modulo 3. Okay. So, whenever you take numbers, for example, from this set and this set, you call it A and B. Okay. That is what you are adding now. You are taking A here and then you are taking B here. When you add them, then what happens? If you are only interested in the remainder, you are saying that the remainder is being just 0 modulo 3. Okay. So, let me introduce this notation. What is A congruent to B modulo n? So, A congruent to B modulo n means if and only if n divides A minus B. So, whenever you say n divides A minus B, you call that A is congruent to B modulo n. Okay. For example, if A is congruent to 0 modulo n, so then that implies that n divides A. Okay. Of course, if and only if. If you think about it, okay, if A is congruent to B modulo n, the remainder that you get from A by dividing by n and the remainder that you get from B by dividing n, they will be same. Okay. So, because A will be equal to some n times q1 plus r1 and then B will be equal to some n times q2 plus r2. So, then what I want to say, if A is congruent to B modulo n, then this R1 and R2 must be same. Why? Because this implies, okay, n divides A minus B. So, that is one thing, and then you can see that that implies n divides the difference between this n into q1 minus q2 plus r1 minus r2. Okay. So, what is the meaning of that? That means n into q1 minus q2 plus r1 minus r2 is same as some multiple of n, and since this is multiple of n, this is multiple of n, this must be multiple of n. That means n divides r1 minus r2, but both r1 and r2 both are smaller than n. Okay. And you can assume r1 is greater than or equal to r2. So, the difference is non-negative and must be strictly less than n, and if it is multiple of n, that forces that r1 equal to r2. Okay. So, that is what I said before. If A is congruent to B modulo n, then that would imply r1 equal to r2. Okay. So, now what we want to do, so we want to say that if I take any element here and then any element here, if you add them, okay, so then you get the unique remainder. So, that is just remainder that when you divide by 3. So, that is 0. Okay. So, let us see that, and then that will actually help us to actually define. So, now we go back to actually general n and then start constructing the set that we wanted, and then we will also define addition there, and then we will see that how this addition actually help us to understand this addition modulo n. Okay. So, let us start with some n, okay, some fix n in n. So, we take it to be natural number because we are talking about division. Nah? Okay. So, now what we do, we take integers. So, note that these integers now it can be divided into small sets related to n. So, you can take all possible multiple of n, that means when you divide by n it leaves 0, then union all possible integers that leaves 1 as remainder, union etc., union all possible numbers that leaves n minus 1 as in remainder. Okay. So, you can partition z into these n subsets, nz 1 plus nz and then n minus 1 plus nz. So, now what I do, I take these sets nz 1 plus nz and so on n minus 1 plus nz. So, this is a subset of power set of z. So, this consisting of n elements, call this as z modulo nz. Okay. So, this is my definition. So, what is my z modulo nz? By definition, this is just these sets nz 1 plus nz etc. n minus 1 plus nz. So, note that each element of this set itself is a set inside your integers. Okay. So, they are not just some elements coming from some set. Of course, they are also elements inside the power set of z, but each one of them itself is a set. That is one most important. So, now if I take any I plus nz, any a inside here, you can see that this a must be congruent to I modulo n. Okay. So, this is actually if and only if. So, this is obvious because that is it is just by definition. If a is inside I plus nz, then a minus I is multiple of n. So, these two are actually coinciding. Now, what we want to do, we want to define addition here in z modulo nz. Okay. So, we want to check that is actually well defined. Okay. So, we are taking this sets and then we want to define addition there, and once we define this addition, then what I want to do, I want to verify that addition is indeed makes this z modulo nz into a group. Okay. So, let us see how one can define the addition. So, if we define the addition the way I am actually already told, so then it becomes well defined by definition. Okay. For example, if I take two elements inside z modulo nz, so then these elements will look like a plus nz and then b plus nz. So, that is how these elements will look like. So, then I want to just say what is a plus nz plus b plus nz. Okay. What I want to do, I just take it to be just a plus b plus nz. Okay. So, this is what my addition. And of course, you may wonder, okay, so the way we wrote the sets, so it starts with 0 plus nz and goes up to n minus 1 plus nz. So, what if I add, okay, for example, if I take n to be 2 and then I may add 1 plus 2z, 1 plus 2z, then that becomes 2 plus 2z. But you can easily see that 2 plus 2z is same as 2z. Okay. This is where this addition modulo 2 comes. Okay. So, let us work out some example and then we will see that this is actually well defined. So, it can happen that let us say when n equal to 5, you may have that 1 plus 5z is same as 6 plus 5z and similarly minus 4 plus 5z. So, you can always add and subtract multiple of 5's. Still that set that we have taken, that will be same. Okay. So, what I want to say, so 1 plus 5z will be same as 1 plus some 5k plus 5z for any k inside integer. This is not going to change. Okay. So, in particularly if I am interested in adding something like this, okay, 1 plus 5z, if I add it with, let us say, maybe let us take 4 plus 5z, I want to add it with 3 plus 5z. So, then what happens? Let us look at it. So, then all you do is you just add those numbers, it becomes 7 plus 5z, but you already know that this set is uniquely determined by the remainder that actually it gives. Okay. So, if you divide 7 by 5, then what will be the remainder? Remainder will be 2. So, you just write here 2 plus 5. Okay. So, that is what you always write now, this 4 bar plus equal to 3 bar is same as 2 bar modulo 5. So, this is another way of symbolically writing. Okay. You take the remainder 4 plus remainder 3, when you add you get 7, but of course, you need to only consider the remainder. So, that is 2. So, that is what you write. So, here I am actually doing it with sets itself. So, that is because this is, I would say, the best way to do it, okay, because this is called what is called quotient group. In the quotient group, the elements itself what is called quotient sets, okay, or cosets. So, we will be adding, subtracting them. Okay. So, now you can see that if I start with any, so what is the meaning of this addition is being well defined. Okay. So, this given one set of the form a plus nz, that may be equal to a dash plus nz for some other a dash, that can happen. Okay. So, that is why when you add them, okay, let us start with let us say a plus nz. It may happen that this is same as a dash plus nz. So, we already seen some example. For example, 1 plus 5z is same as 6 plus 5z. This can happen. So, in that case, if what is the guarantee that if we take a plus nz is same as a dash plus nz and b plus nz is same as b dash plus nz. So, if we take something like this, then we need to prove that, okay, this is what well defined means. So, what is the guarantee that we have to verify? That a plus b nz is same as a dash plus b dash plus nz. So, this is what we need to check. So, this is something elementary, I will leave it to you to check. So, you can actually verify it using elementary number theory. So, basically a plus nz is same as a dash plus nz says that a is congruent to a dash modulo n, and similarly b is congruent to b dash modulo n. From this we get a plus b is congruent to a dash plus b dash, a dash plus b dash modulo n. So, that makes this this addition is well defined. Okay? Because as a set you do not get anything new, you have to get same set. So, indeed if you define it in this way, then this uniqueness is actually, so the well definedness is clear, because this set is corresponding to set that is a remainder of a plus b when you divide by n. So, that will be same as the remainder of this a dash plus b dash when you divide by n. Okay, that is what it verifies. So, now associativity again clear, because associativity will come from associativity of addition that you already have it in Z. So, now you can easily see that n Z will be the 0 element or the identity element. Okay. So, n Z, this is the identity element. So, that is easy to verify, and inverse will be, so if I start with I plus n Z, so the inverse of this, for example, you can take it to be n minus I, okay, plus n Z. Why? Because if you add I plus n Z and then plus n minus I plus n Z, so then you get n plus n Z, which is exactly n Z. Okay. So, existence of identity, existence of inverse is clear, associativity we verified, and we also verified the well defined of the addition that we have defined. So, that means, so this Z modulo n Z with respect to the addition that we have actually defined is indeed a group. Okay. So, like we noted, there could be many representatives for each element of this Z modulo n Z. Okay. For example, when n equal to 5, 1 plus n Z can be equal to 6 plus n Z. Okay, that can happen, but anyway, so that does not matter for us. Okay. So, now we can see one more thing, this addition is also commutative, because a plus b is same as b plus a for all a b in integers. So, that means if I take a plus n Z and then plus b plus n Z, so that will be same as b plus n Z plus a plus n Z. Okay. So, this group is indeed finite abelian group. But note that it is more than finite abelian group. Okay. So, it is indeed what is called cyclic group. So, let me introduce what is called cyclic group. Okay. So, a group G is said to be cyclic if there exists A in G such that this G is generated by the D. Okay. So, here are the examples. For example, if we take Z, then it is generated by 1 and it is generated by minus 1, and there are no other generators for Z. Okay. So, maybe you take it as exercise. So, if Z equal to n Z, sorry, yeah, or generated by n, that implies n is plus or minus 1. So, now you see this other group that we introduced, that is Z modulo n Z. So, it is not hard to show, it is indeed generated by this one specific element called 1 plus n Z. Okay. And we will actually see what will be other generators for this group, okay, but here is one generator 1 plus NHL. So, for example, if you take n equal to 4, you can see that 1 plus 4Z you will be having, and then if you add it twice, so 1 plus 4Z plus 1 plus 4Z, so that is exactly 2 plus 4Z. Similarly, if you add it 3 times, 1 plus 4Z plus 1 plus 4Z and then 1 plus 4Z, so then you get 3 plus 4Z. And similarly, if you do it for 4 times, so then you get exactly 4 plus 4Z, but that is exactly same as 4Z, which is the identity element. Okay. So, this way you can see that all the elements of the group, they are actually obtained. Okay. So, this actually introduces this cyclic group, and then we have seen some examples. So, in the next lecture I will actually determine all possible cycle groups, okay, and then we will also talk about various generators of given cyclic group, okay. So, and also we actually give various characterization of checking a given group is cyclic or not. Okay, I will stop here and then we will continue later in the next lecture. Yeah, thank you.